Okay, so for the sake of today's lesson, I want us to just maybe look at one circle. I don't think it matters which one. I'm just gonna kind of highlight one circle. And I want you to kind of look at this for a second. And if I draw, next. I want you to notice the flower petal shape that's in the middle. Okay, so every one of our circles has this flower petal shape. Now, how many petals are there?
6.
Okay, great. Are they all congruent?
Yes.
Yeah, they are, absolutely. One way I could prove that they are congruent is that I could draw the line from the center out to where that petal reaches the edge of the circle, and notice that it's a radii of the circle. And that's consistent if I did that in every single petal. Okay. So what if I do that right now, right here, from one petal to the one next to it? Would these lines be congruent?
Yes.
Yes. What if I come down here and do this? What shape have I created?
A triangle.
True. Any special kind of triangle?
Isosceles.
Okay, definitely isosceles, we saw that, but can we prove that it is also equilateral?
Yes.
Okay, is this a radius to this yellow highlighted circle?
No, it's a chord.
You're right, it is a chord. But isn't it a radius of this circle right here?
Oh. Wait, what? And the circles are congruent.
Look, and all this, so yeah. Okay, so now I know for a fact that because this orange circle and this yellow circle are congruent circles, we now have an equilateral triangle. Okay, so what if I asked you to tell me how big this arc was? Could you tell me how big that arc, what was the measure of that arc?
60 degrees.
It is exactly 60 degrees. Good job. And how do we know that?
Because it's an equal angular triangle. 360 divided by 6 is...
Aren't there 6 petals? So the distance from the center of one petal to the next petal is 1/6 of the circle. So wouldn't this angle right here be exactly 60 degrees? So we just, with only drawing 19 perfect circles, we were able to figure out an exact 60-degree angle. We were able to create an exact, perfect, equilateral, equiangular triangle from only drawing circles. Now, do you remember when we drew in the height of an equilateral triangle, equiangular triangle? What does that create? Right here. A 30, 60, 90 right triangle. Right? Okay, so that was yesterday's lesson, right? Central angle, arc measure, right there. Today we're going to be talking about chords. So like this radii that we drew was a chord. We're going to be able to talk about the fact that, let's come over here to this chord right here, and maybe one that's not touching it, this chord right here. If we're talking about this circle, we're going to learn today that, and this might be clearly illustrated to you here, if we know that this chord and this chord are equal, we actually know for a fact that this arc and this arc will be equal. And I think that this illustration illustrates that really, really clearly. We are also going to learn, oh, by the way, here's your trapezoid. Okay. Your not just any trapezoid, an isosceles trapezoid. Okay. All right. I am going to go back and forth between just showing you a theorem, and then I have a video that I can show you that sort of does a nice illustration of some of our theorems. It's called the seed of life. Sometimes the smaller version of it, like the 6 circles with the 7th in the center, is called the flower of life. The bigger one is called the seed of life.
What's the biggest one?
And then the biggest one is called like, sometimes it's called the tree of life. Sometimes it's called like this other word that in another language that means like God, essentially. So you can kind of look that up if you want. All right, here is this theorem. Okay, let's go entire page. This is the one I just talked about. In the same circle or incongruent circles, two arcs are congruent if and only if their corresponding chords are congruent. So that's what I just sort of illustrated in that design. So if we had a chord here, and this chord was exactly congruent to this chord, then what we know is that this arc here will be exactly the same as this arc. So we may be able to sort of break up the circle into different sort of sections of arcs and figure out different lengths. So a problem could come to you like this, and therefore we know, oh, this chord and this chord are the same length. So if AB, if this right here is 100 degrees, then I also know that this is also 100. And so the measure from A to C, now careful here. Is the measure from A to C going to be 200?
No.
It would have to have 3 letters. Good. So just be careful with that. Remember, we talked about like there's always 2 ways to get from A to C. This is the shorter way. Okay, so just be aware of that. So that would be this distance right here, which would be 160. Now down here for this one, we have 2 different circles, but do we know anything about how these circles compare to each other? They are, and how do we know that, Elliot?
They have the same radii.
Very good. The radii is indicated as being congruent. All right. And so therefore the circles are congruent. And so if AEB is 260, A to E to B, so if this is 260, then that means that this is also 260, and so therefore this is 100 degrees. Okay? So hopefully, you know, the math, as long as you understand the theorems, the math is pretty easy. As long as you understand those sort of rules and theorems about these things. All right, so this theorem, this one's kind of interesting. This is where I might show the video. All right, let's go back.
Is the perpendicular bisector of the blue chord, and therefore the red chord is the diameter. And it's that simple.
And it's that simple. All right, so here's what we're going to do. We're going to put 2 chords inside the circle, but they are going to actually interact with each other. So maybe I have a chord here, and I have another chord there. So if I have that situation, there might not be a special relationship between those chords. However, if one of those chords happens to be the perpendicular bisector of the other one, so here's one random chord. If this red one happens to be the perpendicular bisector of the blue one, then we know that the red one is in fact the diameter. And that will happen no matter where we draw it. So even if I have a chord like this, if I find the midpoint and I draw the perpendicular bisector, 100% of the time, this will be my diameter. Now, that's huge and important and helpful to us because if we know the diameter, we know the radius, we can find the circumference, we can find the area. We can do a lot once we know that we have found the diameter. So, let's see.
Another way of saying this slightly differently, I've got 2 chords that intersect here. And one of them, the blue one, is a diameter.
So this is the converse.
Doesn't seem to help very much, but if I were to replace that, if I were to make it perpendicular, I would have a special relationship. Let's replace this with one that is perpendicular. And we can see that it is now bisects the chord. The diameter is the perpendicular bisector of the chord. And that also results in the two associated arcs being congruent as well.
Okay, so you saw how he kind of like moved this around. There wasn't a relationship, there was nothing special, but as soon as he made it perpendicular, if he knew this was the diameter and he made this other chord perpendicular, there's tons of stuff we know. We now know that this and this are going to be congruent, and we also know that their corresponding arcs will also be congruent. I think this can be really easily illustrated also if you think about folding it. Just think about folding it over its diameter. You would see that this arc would in fact line up with this arc only if this was perpendicular. So let's fill in those theorems so you have them. So this one is saying, entire page. Okay, if QS is the perpendicular bisector of RT, then QS must be a diameter. So if we're filling in the blank, if one chord is a perpendicular bisector of another chord, then that chord must be its diameter. So if this is perpendicular bisector, then we can conclude it's a diameter. Okay, so that's super helpful. Helpful for us to know when we have a diameter. We also saw that this and this would be congruent, so that can be helpful. I think that's what our next theorem is, actually. So if, in this case, if a diameter is perpendicular to a chord, so is perpendicular to a chord, then the diameter bisects the chord and its arc. So we can mark this picture like this and this would be equal, and this arc right here would be equal to that arc right there. So DE got bisected. Arc DE got bisected. So let's see that in the context of a problem. If we are given a situation like this is super helpful. We know, oh, look, okay, we have a diameter. We have a it's perpendicular to a chord. So now we can start going, okay, this equals this equals this, and we can start finding relationships. So what I can do is I can say, oh, 9x equals 80 minus x. So what, 10x equals 80, so x equals 8, and I can start filling in this picture. So if x equals 8, then this piece right here is going to be 72 degrees. This one here is also, yeah, that one here is also going to be 72 degrees. So what, this is 72. D to E is also 72. C to E would be 144. So then what about C to B to E? Yeah, that would just be 360 minus the 144. So minus the piece that we haven't used. What is that? 216? So really helpful theorems about chords and circles. Lastly, and this one I think is also nicely illustrated by the video. Let me scooch ahead. Okay, yeah.
One. to say the red and the blue chords are congruent if and only if they are equidistant from the center of the circle. And we could visualize this. It could have.
Look at how he can move that.
A lot of different shapes.
And the pieces are all still the same. He could even
like this.
Bring them
They might
anywhere.
have a common point, or maybe just like that.
You could even slide the red one so it's right on top of the blue one.
We're demonstrating this way. It's easier to see. And let's put in some tick marks.
So see, this red one could fit right on top of that blue one. The arcs would be congruent.
The radius drawn perpendicular to the
These are
chord also
bisected.
bisects it. So all four of these components are congruent, and we know from previous theorems that the associated arcs are congruent as well. This is from the previous theorem.
Didn't mean to do that.
From section.
All right, so I do want to show you this right here.
For congruent right triangle.
Okay, look at that. This is going to come up. This is going to come up in your homework because let's say we give you, oh, this doesn't let me draw in here. Let's say we give you this amount, and let's say we give you this amount. Could you find this? Yeah, with the Pythagorean theorem. And why is this valuable? It's the radius of the circle. Or conversely, maybe we give you the radius and we give you one of these legs, you could find the other leg. Okay, so that is going to kind of come up. So here, in the same circle or in congruent circles, two chords, two chords are congruent if and only if they are equidistant from the center. And I would say equidistant and perpendicular from the center. So that's this piece and this piece. And you could also say the arcs here. The arcs would also be, like this, would also be congruent to this. So, when you see a picture like this, if you see that 12 and 12 are exactly the same, if this is 32, then you know that this will also be 32. The 32 is getting split in half. So this is 16, this is 16, this is 16, and this is 16. So Q to R is 32. Q to U is 16. And then for this last one, that's where you might want to consider a right triangle. So if we were to draw this in, take a look at this right triangle right here. Could you find the length of the radius? It's a 3, 4, 5. Very good. Right? This is 3 times 4. This is 4 times 4. This would be 5 times 4. So 20. All right. So that is that's what we're going to see there. And this is the same concept. This has just other multiple pieces in it. Let's see. P to B. So if this piece is 3x minus 17, C to D, oof, if that whole thing is, 15 minus x, and if OQ and QP are 3, okay. You could, in this case, double the blue one, equal it to the green one, in order to figure out pieces. Then, in order to find the radius, you would need to kind of draw in a radii and make a right triangle. All right. Does everyone see that? How 2 of the blue pieces would make a green piece? You could find x. Then you could plug the x back in to figure out how much this is. So you would need to figure out that bottom leg. All right, there you go. So 9-3 is your assignment.